Welcome to our journey into the fascinating world of science. Today, we're going to explore one of the most iconic equations in physics. It's the equation that changed the way we understand the universe. So, fasten your seatbelts and get ready for a mind-blowing adventure. E equals mc². What does it mean? At its core, it stands for energy equals mass times the speed of light squared. But what's the significance of each of these components? Let's start our journey by unraveling the very essence of the universe, energy. Energy is the driving force behind everything we see, from the stars that twinkle in the night sky to the power that lights up our cities. Energy is the ability to do work. It's what powers our world and fuels the processes that make life possible. Think of it as the cosmic currency. The most colossal source of energy in our neighborhood is the sun. It's an energy powerhouse, releasing an unfathomable amount of energy every second. It's like a celestial furnace, constantly converting mass into light and heat through nuclear fusion. But energy isn't just limited to stars. It's all around us, in many forms. Imagine you're bouncing on a trampoline. As you push down and release, your energy transforms from kinetic energy to potential energy and back to kinetic energy as you bounce. Nature, too, is a master at energy transformations. Flowing rivers, crashing waterfalls, and the rustling leaves in the wind are all manifestations of energy in various forms. In living organisms, energy is what keeps us alive. Every breath you take, every heartbeat, every thought in your mind, it all depends on the energy stored in the chemical bonds of the molecules in your body. It's energy that powers the metabolic processes that sustain life. And in the human-made world, we've harnessed and created energy in countless ways, from fossil fuels that drive our cars to the electricity that powers our homes. Our ability to understand and manipulate energy has transformed our world. Now, zoom out for a moment and picture the entire cosmos. Galaxies spinning, stars being born and dying, cosmic rays racing through space. All these phenomena are driven by energy, the fundamental force that shapes our universe. Now, remember our equation, E equals mc²? It's a key to understanding how this energy is intricately tied to mass, and how it can be transformed. But before we delve into that, let's explore another piece of the puzzle, mass. Now, let's venture into the world of mass. Mass is the substance that makes up everything we see around us, from the tiniest subatomic particles to colossal celestial bodies that populate the universe. At the smallest scale, we find subatomic particles, the building blocks of matter. These particles, like electrons, protons, and neutrons, have tiny masses. When they come together, they form atoms, the basic units of chemical elements. Atoms, in turn, combine to create molecules, which can range from the simple, like water, to the complex, like the DNA in your cells. The mass of these molecules determines the properties of the materials we encounter in our daily lives. As we move to a larger scale, we encounter celestial objects like our planet Earth, the Moon, and other planets in our solar system. These massive bodies are composed of trillions upon trillions of atoms, which add up to an astronomical amount of mass. Mass also gives rise to one of the fundamental forces in the universe, gravity. It's the reason objects have weight and are attracted to one another. The more mass an object has, the stronger its gravitational pull. But mass doesn't stop at planets and stars. It scales up further, encompassing galaxies and galaxy clusters. These are collections of billions of stars, each with its own mass, creating cosmic structures that span unimaginable distances. In the grand scheme of the universe, everything is interconnected through the intricate dance of mass, gravity, and energy. The way mass is distributed across the cosmos shapes the structure of the universe itself. Now, remember our equation, E equals mc²? It's a bridge between mass and energy, revealing the profound relationship between the two. But to truly appreciate its significance, we need to understand the speed of light and how it fits into this equation. Now, let's take a fascinating journey into the world of the speed of light. The constant c represents the speed of light, and it's not just any number. It's a cosmic constant that holds a special place in the universe. The speed of light, denoted as c, is approximately 299,792,458 meters per second, or about 186,282 miles per second. What makes it extraordinary is that it's an unchanging constant, the same for everyone, everywhere, and at all times. In a vacuum, like the vastness of space, light travels at this incredible speed. This constant means that no matter how fast you're moving, or how fast an object is moving relative to you, the speed of light remains the same. To put this in perspective, if you could travel at the speed of light, you could circumnavigate the Earth's equator about 7.5 times in just 1 second. It's a velocity beyond our everyday experiences. What's even more astonishing is that light from the farthest reaches of the universe takes billions of years to reach us, yet it does so at this constant speed. The light we see from distant stars and galaxies is like a cosmic time machine, showing us the universe's history. This constancy of the speed of light is not just a convenient measurement, it's a fundamental building block of the universe, woven into the fabric of space-time. It's a cosmic speed limit, and nothing with mass can ever reach or exceed it. This cosmic speed limit also leads to a fascinating consequence of Einstein's theory of relativity, time dilation. When objects move at high speeds, time slows down for them relative to stationary observers. It's an extraordinary phenomenon that has been tested and proven. So, why is the speed of light so important in the context of E equals mc²? It's because this constant c is a central element in Einstein's equation, connecting energy, mass, and the very fabric of space-time. The brilliant mind behind this equation was none other than Albert Einstein. He shook the world of physics with his theory of special relativity, and E equals mc² was at its heart. Now, let's take a step back in time to explore the life and genius of the man behind this revolutionary equation, Albert Einstein. His journey from a young dreamer to a scientific icon is nothing short of awe-inspiring. Albert Einstein was born in 1879 in Ulm, Germany. His early years weren't exceptional academically, but he was deeply curious and independent, questioning the world around him from a very young age. After studying physics and mathematics, he faced challenges in his early career, working as a patent examiner in the Swiss Patent Office. But it was during this time that he developed many of his groundbreaking ideas. Einstein's path to E equals mc² was paved with thought experiments and deep contemplation. In one of his most famous what-if moments, he pondered what would happen if you could ride alongside a beam of light. He realized that if you were moving at the speed of light, time would stand still for you, a concept now known as time dilation. This idea was a pivotal step towards special relativity, the theory that would lead to E equals mc². In 1905, Einstein published his groundbreaking paper on special relativity. It introduced the world to the now iconic equation E equals mc². In this equation, he united the concepts of energy, mass, and the speed of light in a profound and elegant way. Special relativity challenged the Newtonian physics of the time. It showed that space and time were interconnected in ways no one had imagined. Einstein's ideas were met with skepticism at first, but as experiments confirmed his predictions, the scientific community began to embrace his work. Einstein's theories didn't just change the way we understand the universe, they made him a global celebrity. He received the Nobel Prize in Physics in 1921 for his work on the photoelectric effect, further solidifying his place in scientific history. Einstein's life was marked by continued curiosity, activism, and dedication to the pursuit of knowledge. He left a lasting legacy not only in physics but also in the realms of human rights, peace, and education. So, when we explore E equals mc², it's not just an equation, it's a reflection of the incredible journey of a man who dared to dream and challenge the boundaries of human knowledge. To truly appreciate the groundbreaking nature of Einstein's E equals mc², we need to step back and understand the broader context of early 20th century physics. It was a time of incredible scientific exploration and innovation. The early 1900s were marked by the presence of brilliant minds in the world of physics. Pioneers like Max Planck, Marie Curie, and others were exploring the frontiers of the atomic world and radiation. Their work was changing our understanding of the fundamental building blocks of the universe. At the time, classical physics, as described by Sir Isaac Newton, was the reigning paradigm. It had successfully explained many phenomena, but it had limitations. Classical physics couldn't explain certain experiments involving light and matter, setting the stage for a scientific revolution. One of the key challenges was the ultraviolet catastrophe, a problem in the understanding of blackbody radiation. Classical physics predicted infinite energy for high-frequency light, which didn't match observations. Einstein entered this scientific arena and, in 1905, published a series of papers that would reshape the field. His explanation of the photoelectric effect, showing that light could behave as both waves and particles, was revolutionary. But it was his theory of special relativity, published in the same year, that truly rocked the foundations of physics. It introduced the idea that space and time were not absolute but relative to the observer's motion. Over the years, experimental evidence confirmed Einstein's theories, and they became widely accepted. Special relativity, in particular, was a significant departure from classical physics, fundamentally changing our understanding of the universe. Einstein's work ignited intense debates and discussions among scientists, as it challenged long-held beliefs and demanded a shift in thinking. Physics was entering a new era, and Einstein was at the forefront of this transformation. So, when Einstein presented E=mc², it was not in isolation but as part of this larger revolution in early 20th century physics. It was a moment that reshaped our understanding of energy, mass, and the fabric of the cosmos. Einstein's equation tells us that mass and energy are interchangeable. This means that a small amount of mass can release an enormous amount of energy. It's like turning matter into pure power. Let's dive deep into the profound concept of mass-energy equivalence, the core idea behind E=mc². It's a concept that forever altered our understanding of the universe and the relation of mass and energy. In classical physics, mass and energy were considered separate and distinct entities. Mass was the measure of an object's resistance to changes in motion, and energy was the capacity to do work. Einstein's genius was to recognize that these two seemingly separate concepts were, in fact, intimately linked. He proposed that mass and energy were interchangeable, a groundbreaking idea that rocked the foundations of physics. In his equation E=mc², E stands for energy, m for mass, and c for the speed of light. This equation asserts that mass can be converted into energy and vice versa, and it quantifies this relationship. Here's how it works: imagine you have a small amount of mass. It could be a speck of dust, an atom, or even a particle. When you multiply this mass by the speed of light squared, you get an astonishing amount of energy. The implications of this are staggering. It means that even a tiny amount of mass can release an enormous amount of energy, as seen in nuclear reactions, such as those in the Sun. In the Sun, for example, the process of nuclear fusion converts a small amount of hydrogen into helium, releasing a colossal amount of energy. The mass lost in the process is converted into radiant energy, heating our planet and providing light. The mass-energy equivalence also played a critical role in the development of atomic bombs. In these destructive devices, a small amount of mass is converted into a catastrophic release of energy. But it's not all about destruction. Mass-energy equivalence is essential for peaceful applications too, like medical imaging. In technologies like positron emission tomography, the conversion of mass into energy is harnessed to provide critical insights into our health. This concept of mass-energy equivalence is deeply intertwined with the principle of the conservation of mass energy, which states that the total mass energy in a closed system remains constant. This concept of mass-energy equivalence is deeply intertwined with the principle of the conservation of mass energy, which states that the total mass energy in a closed system remains constant. Einstein's equation provides a mathematical framework for understanding this conservation principle, showing that the transformation of mass into energy and back is a fundamental process that governs the universe. So, when we talk about E=mc², we're not just discussing an equation, we're unraveling the deep connection between mass and energy, the key to understanding the profound workings of the cosmos. But why the speed of light? Well, because the speed of light is constant and incredibly fast, approximately 299,792,458 meters per second. This constant plays a vital role in the equation. Let's delve into the captivating world of relativity and, more specifically, the profound significance of the speed of light in this groundbreaking theory. It's a concept that defies our everyday intuition and reshapes our understanding of the universe. The theory of relativity, as formulated by Albert Einstein, fundamentally alters our perception of space and time. One of its key tenets is that the laws of physics, including the speed of light, are the same for all observers, regardless of their relative motion. This concept challenges our classical understanding of how the universe works. It means that no matter how fast you are moving, the speed of light remains constant. This is unlike everyday experiences, where speeds add or subtract. To make sense of this, Einstein introduced the Lorentz transformation equations, which account for the way space and time warp as objects move at relativistic speeds. As you approach the speed of light, time slows down, and lengths contract in the direction of motion. This leads to a fascinating phenomenon known as time dilation. It means that time itself is relative, and it can slow down or speed up depending on your motion. This isn't just theoretical, it's been experimentally confirmed. One famous thought experiment illustrating this is the twin paradox. Imagine two identical twins, one on Earth and the other embarking on a space journey at near light speed. When the traveling twin returns, they find their twin on Earth has aged more. Length contraction is another consequence of the theory of relativity. As an object accelerates toward the speed of light, it contracts in the direction of motion. This means that objects appear shorter when moving rapidly. The ultimate implication of the theory of relativity is the realization that the speed of light is an unbreakable cosmic speed limit. Nothing with mass can reach or exceed it. This not only changes the way we understand motion but also shapes our perception of the cosmos. Einstein's theory connects space and time in an intricate web called spacetime. Objects with mass warp this spacetime, causing gravitational effects. This is beautifully expressed in Einstein's field equations of general relativity. One of the first experimental confirmations of general relativity was the bending of light by gravity, observed during a solar eclipse. This effect showed that even light, following spacetime curvature, could be bent by massive objects. So, when we explore E=mc², it's within the framework of the theory of relativity, which hinges on the constant speed of light and the interplay of space and time. It's a profound shift in our understanding of the universe and the foundation of modern physics. E=mc² has practical applications too. It's the science behind nuclear reactions, nuclear power, and even medical imaging. It's no wonder it played a crucial role in the development of the atomic bomb. Let's explore how one of the most iconic equations in physics has practical applications that impact our daily lives, especially in the realms of nuclear energy and medicine. Nuclear energy, a powerful and controversial source of electricity, relies on the principles set forward by Einstein. Inside a nuclear reactor, uranium or plutonium nuclei undergo nuclear fission, where a small amount of mass is converted into a vast amount of energy. During this process, the nucleus of an atom splits, releasing an enormous amount of energy. This energy is harnessed as heat, which is then used to produce steam, turn turbines, and generate electricity. Nuclear power plants provide a substantial portion of the world's electricity, producing low-carbon energy without the greenhouse gas emissions associated with fossil fuels. E=mc² also plays a crucial role in the field of medicine, particularly in the realm of medical imaging and cancer treatment. In medical imaging, techniques like positron emission tomography, also known as PET scans, use the principles of the equation to create detailed images of the inside of the body. Radioactive isotopes are used in PET scans, and when these isotopes decay, they release positrons. These positrons encounter electrons in the body, leading to annihilation, a process in which both particles are destroyed and converted into gamma-ray photons. The gamma rays are detected and used to create images, revealing the metabolic activity of tissues and organs. The applications of E=mc² in nuclear energy and medicine have far-reaching implications for our society. They not only help address energy demands but also play a pivotal role in improving healthcare and saving lives. As we reach the end of our journey into the fascinating world of Einstein's equation and the cosmic revelations it brings, we uncovered the life of Albert Einstein, we explored the broader context of early 20th century physics, where established beliefs were being challenged, we delved into the profound concept of mass-energy equivalence, we uncovered the significance of the speed of light in relativity, and we explored the real-world applications of E=mc². In closing, we encourage you to continue your exploration of science. The universe is a vast, beautiful, and mysterious place, filled with wonders waiting to be uncovered. The boundaries of science are continually expanding, and your curiosity and passion can contribute to this journey. Thank you for joining us on this exploration. Stay curious, keep exploring, and remember that the universe is waiting for you to unlock its mysteries.